I'm Travis. So I'm also known as TiKevin83. I'll just say quickly a little backstory on that, because many of you might be confused why it says Kevin if I'm Travis. The reason is my best friend Brad has a cousin named Kevin. We always played Pokemon together growing up, and we borrowed his cousin Kevin's cartridge to play Pokemon Emerald. So I would often be Kevin when I was playing Pokemon. So I'm now TiKevin, and I also do code golf challenges and TI83 Basic. So it's TiKevin83. So that's a little backstory on the name there. But we're going to do an overview tonight of all of the web technology that I use in my hobby speedrunning projects. So we're going to do a little live demo soon here of what I actually show off at conferences. They talk about like games done quick, and I was talking with one of the other attendees about LTX we were at last August. And we're going to be at the Midwest Gaming Classic in just a few weeks here too. So we do a lot of conferences like that showing speedrunning technology. And today we're going to talk about some of the web technology that's come out of everything we found doing these speedruns. So, okay, we're going to do that. What is Pokemon first? Some of you might know what Pokemon is, so we're going to make sure to get to that too. Then who the heck am I? We already did it. We don't need to do that. What is speedrunning? We might need to do that, so we're going to do that. And then we're going to show the verification, and then we're going to talk about web tech. Okay, so what is Pokemon? Pokemon Yellow is one of the games I play, but Pokemon in general is the largest grossing media franchise, period. It has totaled $80 billion, mostly off of merchandise sales. And for comparison, Mickey Mouse in second has totaled $52 billion in total sales. So, very, very massive franchise. Pokemon games are RPGs that involve catching, trading, and dueling a fictional universe of wild animals known as Pokemon. And there is a popular long-running anime tie-in TV show and many spin-off movies associated with Pokemon. So Pokemon Yellow, one of the games that I specialize in doing speedruns of, and we're gonna explain what speedrunning is too, so don't worry, we gotta get that too, but I specialize in it. It's a tie-in game that they created to make the first generation of the video game a little bit more like the anime that they were producing at the time. So that's Pokemon. And each of the 9 generations of Pokemon now are based in a different region of Japan. So like Kyushu province or Honshu, different islands on Japan have maps to different generations of Pokemon, and they've also recently got Spain and the UK and some other areas of the world. So, me, I'm TiKevin83. One of my friends made this lovely little Bitmoji of me, and I'm a speedrun record holder actually in Pokemon Yellow. I have the record in the tool-assisted speedrun of both glitchless and no save corruption. And there's another category called save corruption, which is even faster than those two, which I do not have a record in because it's much more complicated. I'm an official ambassador for TASVideos as well. So TASVideos is a site that hosts records of speedruns, and I talk about what contents do that. And I'm also an administrator with TASVideos. TASVideos is a team that takes stuff that's archived on TASVideos.org and shows it at those live conferences, with the additional condition of it being on live original gaming hardware and not in emulators. So we'll get to that. So we talked a lot about speedrunning already. What is speedrunning? Speedrunning is playing video games often, but not necessarily retro games, with a timer running to track completion time. And speedrunners add these arbitrary goals to games to enable timing different potential categories of different lengths, i.e. like you might actually be in the game, or you might be in every collectible getting 100% complete of a game. So we have all these different categories, all the different arbitrary rules for speedrunners to be able to make these like special timed categories. And then sometimes when we do speedruns, we need tools to help runners evaluate the quality of the run. So they want to know in real time, hey, if I keep doing this run, am I likely to get a world record or a new personal best, PB time? So we've built tools in websites to help make speedrunners go faster or make sure that they're going faster than they have before. And then the next thing we need to get into is not what is speedrunning, but what is tassing. So if speedrunning is playing a video game fast, tassing is playing through a game perfectly. And it does that by taking a game and slowing it down to go frame by frame. And we do that by, instead of playing the game live on the hardware, we built an emulator that is perfectly accurate to the original system, to where stepping through it frame by frame shows the same frames that you would see if you played the game live in real time. And that allows you then in the emulator to pause, go back, and change and fix your mistakes to build a perfect run. Often it's not actually perfect because if you do the math, like 8 inputs on a controller, even on the NES, to the power of however many frames you have, that's more than the number of atoms in the universe. It's not actually perfect, but we get very close. And there's been some shorter ones like Dragster that have had mathematical proofs done of the actual fastest time that just prove cheaters and such. So that's a fun topic too. But for the purpose here, just tassing is taking those speed runs and slowing them down frame perfectly and making perfect records. Then TASVideos, which are a representative, is a site that aggregates and tracks those records so that we can have a kind of collective understanding of, yes, this is the current record of this game, and the community all agrees on at a specific time. And you can kind of see here, a player piano. This is an analogy I love to use to explain what tassing is. A player piano is a piano where there's like a roll of the keys that goes through, and the piano will play itself by seeing what holes are in the paper. And it's basically exactly the same thing with tassing. There's a roll of inputs, and it's going to be 0, 0, and then, oh, maybe the stick needs to be 100 degrees for this frame, and 120 degrees the next frame. So you can kind of see how it's analogous there to a player piano. Okay, so we've talked about speedrunning and we've talked about tassing, but now there's a whole new layer, task verification. This is what TASVideos does, we show at conferences. So going from tassing to task verification, we're designing controller interfaces to inject inputs into the original console. So once we've built the task, the script of that piano roll of all those perfect inputs, we can then convert it into a format that the console will actually recognize and play it back on the original hardware instead of an emulator. And TASVideos is notorious as a mascot for that process. We do that often at GameStop events. And I think we've raised over like $1.3 million for charity now between Red Cancer Foundation and Doctors Without Borders. So it's a great charity thing too. But another really cool thing also with task verification is that those scripts then, when they're verified, can act as test ROMs for emulators, because emulators need to know whether or not they're accurate, and if you can then take that thing that you've proved is exactly the way the console worked, and then play it back in the emulator, you get an additional layer of kind of like a unit test for your emulator that can play back the input script the same way the console works. So, all that being said, we're going to do it live. We're going to show you the task verification live. So, right now, we are in Pokemon Coliseum. Pokemon Coliseum has a buffer overflow exploit in its save data. So I have a very special crafted save on the memory card in the front of the GameCube that I've injected from a Wii. So I have a Wii that's hacked in my house, and we inject the save data from the Wii. It's way easier to hack a Wii than it is to hack a GameCube, because it has internet access, and you can just go to a website and go here. So we have then the GameCube with the hack save files. Now we're going to play through Coliseum up until it loads our first Pokemon in our party's name. And that name is longer than the game developers intended to be possible for being displayed. They assumed that you could only input so many characters, but they stored the actual name as much longer than the buffer they made available for inputting characters. So there's this bug, if you go over here into a specific fight, and get that name to show up, that the game will crash. But it will, very conveniently for us, crash in such a way that gives us total control of the game. And by total control, I just mean we could play any program we want from there. We could inject any program you could ever write. Cool trainer book. So once we're in there, the second memory card slot is going to come into play. Go ninja! And now we have total control of the game. So this is Swiss. This is a homebrew data manager for the GameCube that lets you play whatever you want. One of the really cool things you can do with it is you can put an SD card with every GameCube game that was ever made on the front of this GameCube in one of the memory card ports. And it will emulate the disc reader, and you can play literally any game without having to reset your GameCube or anything. It's just straight there in the front of your GameCube, no disc. And this is all also with completely original, nothing we've done is non-original hardware. We're all still in completely original Nintendo hardware. Even the SD card reader was a Nintendo accessory designed for use with Animal Crossing games. So we're completely using Nintendo's system to hack this up. Now that we're in total control of the GameCube has an accessory at the bottom of it called the Game Boy Player. This is not just a normal GameCube, it's a GameCube that has the Game Boy Player attachment. And the Game Boy Player attachment itself contains an entire Game Boy Advance. And the Game Boy Advance, for backwards compatibility reasons, contains an entire Game Boy Color, which backwards compatibly supports the Game Boy, which we can perfectly emulate. It's a lot harder to emulate newer stuff than the Game Boy and Game Boy Color. We're working on it for Game Boy Advance a little bit, but the Game Boy and Game Boy Color we can do. So the practical upshot of all that is I can play a replacement software we built for the Game Boy Player startup disc because the GameCube needs to know how to talk to the Game Boy Player. The replacement Game Boy Player software will allow us to read inputs from the SD card to then play the inputs from like the piano roll. This guy here has the piano roll for the task. Okay. You want to do it? You want to see it?
Yeah.
Okay. We're going to do Kirby's Dream Land. Pull out the controller. Nothing is touching the game. You can see in the upper left the input viewer, and that's the input that's reading from the input log right now live. And you can see too, Kirby will often vacuum in enemies. The GameCube can only show so many sprites at a time, and even if it's showing all the sprites it can, even that's too slow. So the tasker is sucking in enemies to make the game engine run faster, because so many sprites can overload the game engine. You can also see a lot of damage boosts and stuff where he's getting damaged by bosses and then smashed forward in the game. So we'll just enjoy this for a few minutes and then we'll switch over. If I showed the whole thing, it would take 20, but we don't need to get into the whole thing. I just wanted to show you guys this is possible. Does anybody have any questions or observations or anything while we're watching here? Go for it, Matt.
How did you all figure that out? Inject that.
There was a guy named Fix94. He found the series of exploits. I think it's an issue actually in like a standard SDK that Nintendo made for games. So if there's a whole bunch of games that have a very similar named exploit that you can inject. Melee has a similar exploit. Twilight Princess, 007 Agent Under Fire has the fastest one. So, and that's great because, or maybe not the fastest, but one of the fastest ones. And that's great because it's cheap. You can buy the Agent Under Fire for $20.
So in the speedrunning community, why not just use a hacking way? Is it because it needs to run natively on some kind of hardware and it's just hard to demonstrate and validate with a regular piece?
With an actual Game Boy? Yeah. So it's like way more complicated. You need to open it up, solder onto the input lines, and then build a microcontroller that can send things. And then you also, one of the crucial things that makes this all work is that the Game Boy Player sends up audio data and video data over a bus to the GameCube. And we need to know internally how fast the Game Boy is running. So nominally that would be about 4 megahertz, or 4 megahertz I think it is, it's like 2 to something. So nominally it runs at a certain rate, but every single manufactured piece of silicon oscillates at a different rate. And they don't run at exactly the manufacturer rates. You can see that even now with your modern chips, they don't run at exactly 5 gigahertz, they're going to run at 5.01 and 4.99, flop all over the place. So what we do to be able to know exactly when we're supposed to send the input is we watch how much audio data we've gotten from the Game Boy Player, and then use that amount of data to know when to send our input.
Amazing.
Yeah. Sloth is a question.
Yeah, Travis, are we watching a speed run right now?
Yes, this is the fastest possible run of Kirby's Dream. And it's all being done on the original hardware. And just remember, the Game Boy player attachment is a Game Boy Advance. It's not like an emulator of a Game Boy Advance. It's an actual, has the same hardware as a Game Boy Advance does. It just has some changes that the video and audio get sent over to the Game Boy response instead of to an actual LCD. I was playing League of Legends back around like 2016, 2017. I love the lab. It's great. The community is not amazing for League of Legends, but I wanted to stream stuff, and one of the things I found watching around streams was people streaming of playing Pokemon Yellow. I had played Pokemon Yellow when growing up. I still use my original cart for it in these demos. We wanted to watch a Pokemon cast, and yeah, so I got into it that way, and then I got from playing it by hand, I got to like 3rd or 4th of the leaderboards playing it by hand, and my hands started hurting, and I was like, I don't want to get arthritis, so I switched over to tasking, which was no less arthritis than
Yeah.
And now I do this, I'm more focused on doing these talks or making websites than doing the actual tasking of these things. All right, so that's tools to speedrunning. Okay, so now that we know what that is, we're going to watch some tools that we use for helping speedrunners do things and also preserving the video that we get out of speedruns for TASVideos.org. So static microsites using TypeScript and or React are super easy to spin up, GitHub pages, GitLab pages, and things like that. And we can use them to re-implement many tools that were previously written in Java 7, Java 8 for other parts of the web. So a lot of it was also closed source and not as accessible back in the day. So the first thing I'm going to talk about is the Gen 1 catch rate calculator. There's a problem in the random number generator for Gen 1 Pokemon games. And that is something called rejection sampling and deterministic seeding. So if we follow along with how this works, okay, where I talked about we're watching an amount of time the console has been on to know when to send inputs. And if you follow that to its logical conclusion, it means there's got to be randomness in there, right? Well, the randomness will always act the same way from the same amount of time the console has been on. So in a practical sense, there's no actual randomness in anything. In a computer, it's pseudo-random. The random number generator in Pokemon Gen 1 uses that clock of how long the console has been on to seed its random number generator in advance. It doesn't use like a Mersenne twister or any other actual like algorithmically sound thing. It just takes how long has the console been on, and then at the next frame it says, oh, how long has it been on, add that to the previous value, create a new number. And it looks kind of random, but if you have played Pokemon Gen 1 and walk in circles with the grass, it's not random. You get the same encounters over and over again, and it really doesn't work as well as you hope. So if you dive into it, you can see the problem is that this should look like one color that's like a mosaic. Like all the colors are like interspersed. Like if you get like a 0 in the random number generator in one spot and the second time you call it, those two things are not correlated at all. Like in a random number generator, you don't want the previous value to influence the next value you get where it's not random. So if you see like one axis, it's one call, and the other axis is the other call. If you're seeing patterns in here, it means those two things are tied too closely. So what we figured out is that the problem is that there's a rejection sample. So when you choose to use a Pokeball or a Great Ball or an Ultra Ball in the first generation Pokemon, those balls will give you a better chance of catching the wild encounter. The Great Ball and the Ultra Ball first restrict your random number to be like 0 to 150 or 0 to 200. And if it's restricted to be a certain number, it can't be the other numbers. And then if you say like, okay, let's say 201 from a Pokeball always maps to getting a 2 for the second call because of how the random number generator works, then that 2 would mean you would catch it. Well, you can't get that. You can't get that number because it's just rejected away at 201. And then let's say 202 maps to 7, and then 7 would mean you don't catch it. Well, that's also been rejected. So the practical upshot of all of this is that the rejection sampling means that for a lot of Pokemon, it's way harder to catch them than you would intend because it's rejected away numbers that would lead to you catching the Pokemon if it worked out. Please ask questions, because I probably just spewed a bunch of very technical garbage about how random number generators work.
Can you explain the X and Y axis again of the?
Yeah, so like, imagine you're like called random in like your JavaScript line, okay? And you get like 10 as your number. There's no 0 to 1, so there's going to be you get 0.5. So imagine like you get 0.5 here, and then you call it again. So this is like your second line, you're calling it here, and you get like 0.7. So what you should see if this is truly like pseudo-random is all the colors like intermixed and no like obvious pattern, just like a noise. But instead you see like, oh, this whole middle part here, if you get a 0.5 on the first roll, then the second roll, it's not going to get you a catch. So, yeah. So we built a tool in the web browser that runs through the actual like Game Boy assembly code, or a translation of it to JavaScript, for every possible random number, and like discombobulates those correlations. And we do that with web workers. So we actually spelled 16 different web workers, one for each thread or HP value. And then it goes into the threads and looks at all the different other possibilities of random numbers that could be influencing the catch. And from all of that, it spits out numbers of what's possible. So this is a common pattern you'd see for web workers, where I say, hey, go do a bunch of math out on this promise, and then post the message, and then we'll get it back. So web workers are super useful for threading things in the web if you ever need to do actually truly multi-threaded work. Because if you just do a promise, that's not actually getting you off the main thread in JavaScript. You're still on a single thread in promises. You need workers to get into actually having multiple threads. And then we can resolve all the promises with promise.all. And then this is what some of the actual math of the RNG calculations actually looks like. We're looping every possible RNG byte 0 to 255, and a byte is 256 numbers. And then we're looping through every possible internal state of the divider, which is that timer of how long the console has been on, that we use over in the TASVideos land. And then once we loop through those things, that can generate every possible state of the RNG and see whether or not it would lead to a catch. So in the website, you get two values. This is the value that like Bulbapedia would spit out for what your probability of catching the Pokemon would be. And this is the value that the site actually calculates based on how the random number generator actually works. And all of this came about, and this research came about because a guy named Xarian was doing a run called Ash Percent, where it's basically like cosplaying as Ash in the first season of the anime, and going through and being like, okay, so I need to catch a Butterfree, and I need to release it, or I think it's release a Pidgeotto. I don't quite remember off the top of my head, but you're doing all the steps that Ash would have in the anime. One of those steps is catching 29 Tauros, and he was doing the math on his attempts of like, wait, I've been catching like only 6% of the Tauros I've encountered, and it should be 10% if I put my number in Bulbapedia. Why is that? So then we built this to show, oh yeah, it's because the random number generator doesn't work. One of the other cool things in that space that we worked on was assembly script. So you guys probably know about TypeScript as web developers, but there's something called assembly script, and that lets you directly write WebAssembly code, like or bytecode, in a TypeScript-like language. So you can like annotate your thing as a uint8 or a uint16, and not just a number, and then it will translate it directly into WebAssembly instead of into TypeScript, and that allows even more optimization than just the threading. It turned out that we were able to do other optimizations and not need that crazy level of optimization to get the site to work fast enough. But that's another cool thing. If you need like crazy high performance web code, you can write assembly script. Cool. So that wraps up the catch rate calculator. There's another cool thing in Pokemon that I wanted to talk about, a little web tool we built called the Gen 1 classic DV calculator. So in Pokemon, DVs in the first generation are like genes. They kind of determine how good or how bad a Pokemon is. And the DVs are 0 to 15, and they map to the later generations IVs, which are now 0 to 31. And the way they did that, I wish I could, can I move this? Yes, okay, sweet. So the way they did that is they called the RNG twice, and and they took the first half of it to be the attack, and the second half to be the defense. And then the second time they called it, they took the first half to be speed, and the second half to be special. Those are different like stats that are relevant to a Pokemon. And then they took the last bit of every number they called, and they created another nibble of 4 bits for the HP. So that's how the data is actually stored internally. But we need to know those numbers almost as soon as possible when we catch a Pokemon when we're doing a classic speedrun. There's a category of the Pokemon speedrunning community called classic, where we don't allow the RNG manipulation that's possible by playing the game perfectly, like we showed in the task. It's actually possible for humans to play that perfectly in Pokemon for a few seconds, the game starts up, and then get an encounter right away in the game, and get an exact Pokemon they want, because there's these things called buffer windows, where they can hold an input through the buffer, and it will always happen on the same frame, and then they go into the game, and you get the same Pokemon every time. So in the classic category, that's bad. It's like, oh, it's too powerful. You can't do that. That gets your Pokemon perfect. It's not fun. If you're playing with the same Pokemon every time, it's like, okay, I don't have to think at all. I just destroy this thing. It's always do the same amount of damage. It doesn't do quite the same amount of damage, but it always does more damage than you ran. So some people are like, I want to run the classic category, and then they need to be able to calculate their DVs on the fly based on what they see. So I think I talked about all this stuff. Yes, so the next key thing here is the actual site. So when you catch your Nidoran to win a round of Pokemon Yellow, because Nidoran's the most powerful Pokemon at the beginning of Pokemon Yellow, it'll have some of these stats for its HP, attack, defense, speed, special. So you click on like, oh, it has like 12 attack, 9 defense, 12 speed, and 9 special. And then the site does a bunch of math to figure out which of those are actually like possible DV combinations. Because for example, if you had 23 HP, we immediately know you had the high bit of every one of the other numbers, because you must have had like, if the attack of your last bit is 1, then that's going to add 8 to the attack DV, or the HP DV. And then if you go to this defense, it's going to add 4. So we know it must be at least attack has the last bit is 1, defense is the last bit is 1. So the site does a bunch of math in the background from all these bits, and then figures out, oh, these are your DVs, like immediately, without hardly having to do anything beyond just knowing the stats that you see in your screen. So that's super, super useful. And one of the things I want to talk about when I built this site was PUG markup. I love PUG. I wish it was used more in static websites. It's this HTML templating language where you don't have to write like end tags. You just write like dot container and it translates that to a class, or h1 space, and then it treats that as your h1 tag. I love how terse it is. I wish there was more ways of doing that on the web. So I love using plug in that, and then also you can see some of the internal math in plain JavaScript. In plain JavaScript to remove those bits, you can see we wrote like remove a number that has this bit, and then there's an array of bytes, and it removes bytes that have certain bits. So now, okay, this is what I really love talking about for conferences like this. So RGBScaler.com. So if you feel like you've been overloaded with information, you might want to leave now, because we're gonna get into a whole other layer of complexity here. So the first thing we're going to talk about, with a bunch of problems we have with archiving video for TASVideos, is called chroma subsampling. So we got to go back to the days when they had black and white TV. When they had black and white TV, they were like, we want color TV now. And when they added color TV, they wanted backwards compatibility. So instead of having red, green, and blue like our eyes detect, they decided, why don't we translate that to a brightness component, which would still be used for the black and white TVs, and then a difference between the brightness in blue and a difference between the brightness in green, and you could use those three numbers to reverse engineer red, green, and blue for newer color TVs, but then the older ones could use the brightness signal alone and ignore the other two channels. And then somebody else came along after that, after color TV, was like, oh my goodness, I know that humans are more susceptible to differences in brightness than they are to color. So if we reduce the frequency of the color data, we can transmit more data along the cable lines for like high resolution data for the brightness and that get better quality. The problem is they weren't thinking forward about how signals would go now. So now even today, almost any video you watch online will be encoded in that way of brightness and the difference components and not actually red, green, and blue. So this is a huge problem for preserving and restoring game footage, because game footage is going straight from a game console to a TV. It doesn't care about needing to save data over all of these cable lines all over the country. So it goes straight red, green, and blue right to your TV. So if for example, you needed to archive footage of an NES in 240p, that 240 wide pixels is going to be, well, every pixel is going to be a red, green, and blue component. But if you were to save it the way that a video normally is saved on like YouTube in 240p, you would have the right brightness information for every one of the pixels, but for every like quadrant of 4 pixels, it would have that to only having like one shared color value for that set of 4 pixels. And we'll see in the next couple slides what that looks like in practice. The second problem is stretched aspect ratios. So games back in that day did not actually output a specific number of pixels. It was more like we have 240 lines of pixels and we're going to paint them for a certain amount of time across the screen. So there was no concept of a certain specific resolution that your game should run at. It's not running at 240 by 320, it's not running at 240 by 280, it's running at 240 and then just however long your display is for the CRT. So the games actually ended up having rectangular pixels because they would paint a little bit longer than they would be tall. And obviously displays do not have rectangular pixels. Each pixel is just a tiny red, green, and blue dot. Or it gets way more complicated. We don't need to get actually into how the newer ones work, because sometimes they have white dots, sometimes they have these like quantum filters. But the older displays, they didn't have pixels, they were just shooting a phosphor beam at a cathode ray tube, and it would paint a little bit longer than it was tall with the beam for each pixel. So we can't really replicate that very effectively on modern screens because they have square pixels, so you get another kind of artifact of these pixels not lining. Then we also have to talk about upscaling for display presentation, because 240p is probably like this big on the screen, and you gotta get it this big to be able to see it. So if you're upscaling it, we have to use an algorithm for upscaling. There's a really common one used called bilinear, almost everywhere on the web, and it's used that way because it's really power efficient. Like if you're using like a phone, watching a video that's like 240p, upscaling on your phone with bilinear, you're not going to hardly lose any power. But it looks terrible for video game footage. Really, really terrible. So we try to use different kinds of upscaling algorithms for preserving our video game footage, like sharp bilinear, or sometimes called area, or nearest neighbor, where it looks blocky, stuff like pulls up. And then there's 2 more things. Lossy compression. Lossy compression is when you have a video and it looks degraded. You might see like speckles or other artifacts in the video that are you can kind of see that like you know, like the do I know what a JPEG is meme? It's also sometimes called deep fried memes, where they look like really just artifacted. That's lossy compression, and it happens often in like photos like JPEGs too. Lossless footage, where you don't have that problem, is not widely supported on the internet, but there are 2 newer codecs, H.265 and AV1, which respectively can be used on iPhones and Android phones, which support lossless footage, so we can use that with RGB scaler. And the last problem, okay, so we have all these problems. Some of the artists for old video game consoles were really smart. We're like, hey, if I know about these things, then I can make art based on what I know is going to be degraded in the signal, and then it'll look the way I want afterward. So sometimes, if you're trying to preserve a game accurately, you need to not just actually like get rid of all these problems, but actually cause some of them again to make the art look correct. A common thing that shows this is called dithering. So imagine you have like a 256-bit color display. It has that many colors. You want more colors. So you say, okay, I know the colors are going to blur together on nearby pixels. So if you want like a color between color 255 and color 254, you say, okay, I'm going to put 254 here and then 255 here and checkerboard it. So you see this thing that looks kind of like a checkerboard in a lot of old games. That's dithering. Because if you played it on old CRTs, it wouldn't look like a checkerboard, it would look like a kind of smooth blend of color. So, the thing on the left is one of the first Zelda games, and Link has his shield, and it's a little bit bigger than on the bottom one, and that's because we're using point scaling. So point scaling says for every pixel in the source, we're going to try to use that same color somewhere in the output image. So we're not going to have any blending like in bilinear. Bilinear says I'm going to create a smooth gradient between the colors that are possible in the source image. And then over here on area, it says, okay, if I have a source image, I'm going to use the exact color if I can. But if I have a pixel that doesn't quite line up right, where like maybe it needs to be like the 4.5 pixel, I'm going to blend on that one. So you see, in this area one, Link's shield is the same size at the top and the bottom. But in the nearest neighbor one, his shield is bigger on one frame than the next frame when he's moved further. Because it needs to map to an exact number of pixels. So we generally like this area effect because it's as good as it could possibly get for your screen, and then it also preserves shapes. I kind of liken it to the Mercator projection in maps, where like you have these like really stretched continents that it's preserving the longitude and latitude lines, but the continent look all wonky. That's what's happening with the point scaling. Okay. So what we did was we used a WebGL2 canvas to implement custom scaling algorithms that do all this stuff correct for older retro video in the canvas. And so it's terribly power inefficient, and you never actually want to do this, and it's very experimental. But it makes it look correct. So you can kind of see here, this is what happens to Atari dragster footage if you have all of these problems happen at the same time. You can kind of see, there's just like a lot of blur. You can see there's kind of like these artifacts happening. There's like white bits next to the 5 and 7 that shouldn't be there. And if you get everything correct, it looks more like this. I'll just flip back and forth a couple times. And this is what we would try to aim for when we're doing web preservation in this video. And then there's another layer. I talked about some games like intentionally try to work with the way that the screen would damage the data. So we also have CRT simulation, where this is layering over the phosphor mask that would happen on an actual CRT to kind of blend the colors together. So if you go to this QR code on your phone, you might be able, this is very experimental, you may be able to see on your actual phone some of the same technology for a specific speed run that we've archived. And I'll play it up on the screen here too, so we can all see it. This, you guys hopefully are seeing the same thing on your phones. If it works or it might not work. It's very experimental. But the basic idea is this site is scaling this footage of Teenage Mutant Turtles exactly for what this display could possibly show you. So this is probably the sharpest footage of NES you've ever seen. It's impossible to get any sharper. So yeah. And we're trying to go back slowly and do some upscaling for more videos than just this one. I did like a bowling task too, but this is so experimental and so niche. We are still kind of thinking through exactly how we would want to go back and do this for, if we went back through a whole archive of every game we've done for passing, and it was happening. So it's not been done for everything yet, but we have the proof of concept that you could actually do this, preserve retro footage on CRISPR. Cool. Any questions over here on this one?
I missed the part, I don't know if you said it, where the source of the archive is just a file that's uploaded in a specific format. Is it all a specific format?
Yeah, it has to be an extremely specific format. So it can be AV1 or H.265. Those both work losslessly on the web. You can also use H.264 lossless. All of the files I'm talking about have .mp4 extensions, except for AV1 has like I think it's a WebM container format, but H.264, the only browser that supports it properly for losses on the internet is Chrome on the desktop, And the reasoning behind that all is that your phones, they only have decoders for a very, very small subset of all the possible videos that you can make. So that they can be, I was talking about like power efficiency, that's the main idea. Is like, if they do this like really small subset of H264 videos, they can be really power efficient with that subset, and then it'll look worse, but then nobody will care or notice because the phones are really high resolution, they use AI to upscale stuff down. So, but they're not targeting those technologies for retro video, they're targeting them for film footage usually. So. Alright, so one final thing. Little last treat for the show today. We have been building a new website for emulating the Game Boy in the browser. It's called T3Boy, after the T3 step. If you ever watch Theo, he does his T3 stuff. And T3Boy is a copy of the exact same emulator we use to make all of these console-accurate speedruns, but it runs in the browser. And we do that by using Emscripten. So Emscripten can take C code and emit a WebAssembly binary that has that same C code. And then we can hook into the C code in our website in React and use effect hooks and stuff and drive the emulator in a website. So I have already picked out Pokemon Yellow and a BIOS format. So this is very important for legal reasons. This site does not host any proprietary Nintendo technology. You have to have your own copy of the game and the BIOS, which are very proprietary to Nintendo. And you can also upload an input log, like I was showing for the piano roll on the GameCube. And once you have those things uploaded, let's refresh them. Sometimes the game doesn't work quite right if you don't refresh the page first. I'm just going to double check here, refresh it, pick my input log, and then go down here and click play. I have to manually click play because there's this stuff now where browsers don't want like Fox News or CNN to autoplay audio for you when you go to a website. So this relies very closely on the audio system of the site to work. So you have to manually click the play button for the emulator to start. And the buttons are touch input compatible. So if you go on your phone to t3boy.versal.app and you had all these files, you could play on your phone with the buttons. And this is doing exactly what we were just doing on the GameCube. It's verifying that this emulator is as accurate as the actual GameCube and Game Boy player combinations. Which I'm super excited about because it's an entirely new era and level of accuracy in website emulators. So, if you guys are cool, I can show a little bit of code behind that I was talking about with the use effect. So the T3Boy is the repo where this is hosted, and if you go into the source pages and index, you can see this is all written in like your standard Next.js website. But when you go down into your things like use effects, we are wrapping C code from Emscripten to pull out functions like how do I check the revision of the library we're going to remove, or this one creates the actual instance of the emulator, or load buff and load buff. These are the functions that let us inject the ROM and inject the BIOS into the emulator. And once we have all those functions pulled out into state hooks, we can then go down further and run the actual functions and call them into C in our render loop. So like down here in the render loop, we get audio back for our context, put it into the 2 channels of an audio buffer, and then at the bottom here, it's a request animation frame loop. So this is key. I use the same thing, the same technology and concepts of a request animation frame loop in RGB scaler and on T3Boy, so that it's only rendering a frame as often as your device wants a new frame. It's not saying like every 1,000th of a second, hey, Chuck, we need a new frame yet. It's only doing that if your display is potentially new frame. So, yeah, that's T3Boy. And if you want, I have these cool Discord invite links, and you can come chat about more in Discord. Thanks so much. I would love it if people contributed to it. It'd be very helpful.
Yeah.
One of the things I don't have quite wired up yet is I've had trouble figuring out how to initialize the scripted library and then have it, because like it's a WASM binary, and I have to right now basically say wait 3 seconds when the site starts up for the WebAssembly to be compiled. But there should be a way to get the scripted output to emit like a waitable promise that you can say, hey, start up, and then when it's started up, then go do all these use effects. But I haven't quite figured that out yet. So if somebody wants to come in and hack that together and improve the site, that would make it start up a little bit. Yeah, it's basically what I'm doing right now, but I'm waiting 3 seconds to do it instead of telling it to start itself up and then. Yeah. There's a lot of other ways to there's like probably 3 or 4 different ways to tell scripting to do the build. There's like a web targeted, there's a single file, there's a bunch of options. So there's stuff I'm thinking about there. So, yeah. Any other questions for go for Matt?
What did you do again to take C code and put it into like something?
And scripted is what it's
And
called.
scripted.
EM scripted.
How does that work?
It's basically, what's it called? So it's not GCC, it's an LLVM.
Okay.
It's an LLVM like bytecode interpreter that's like, it uses LLVM to compile C code, and then it turns the LLVM bytecode into WebAssembly.
I see. And then what you're showing us here is actually pulling in a file that reads it.
Yeah. Yeah, it's already loaded the file like into the browser, and this code here is just doing all of the like Next.js boilerplate that you need to do to like create a render loop and then call into the C library during the render loop.
Slightly ignorant. Is that code, the C code, executed in the browser?
Yes. There's a sandbox called WebAssembly. So they created this because scripting used to compile to JavaScript. And I talked a little bit about how JavaScript is like a single thread. If you do anything on the JavaScript main thread, nothing else can be happening. You can't, like I was showing you guys like buttons changing colors and stuff. If you're on the main thread, none of that can be happening because the main thread will block rendering nothing will update the state of the page if you're on the main thread. So what they did by implementing WebAssembly is now you can compile to that and it can run in its own little sandbox, and the main thread can call out and say, hey, go do something WebAssembly, and then wait and do other things instead of being stuck. Yeah.
Right.
Yeah. Cool. Well, I'll be up here if anybody wants to see more tasks. I can show yellow stuff too, and I'll be around. Thank you guys so much for listening. It was great.